All right, so sorry about that. Discombobulated. Okay, so luckily we did accidentally start these the other day, so we'll just pick up where we left off with looking at actually using data to calculate the rate of either the appearance of a reactant. Again, red is the reactant. I'm sorry, the appearance of B, the product, or the disappearance of A, the reactant. So, as I was saying the other day, before I realized this wasn't the right notes, we could do it for the whole 40 seconds, we could do it for the first 20 or the second 20 seconds. So you could do it for any amount of time, and as we get more into this chapter, we'll look at, you know, the rates do change because as the amount of the reactant disappears, there's less reactant, it's going to slow down the reaction. So you know, we can look at any rate. If we just look at the overall, so the first one, the appearance of B, we're going to take the change in concentration over the change in time. Let's grab marker too. So if we want to do for the full 40 seconds, we can look at the total time of 40 seconds. And then for B, we're going from 0 to 0.7. In this case, it's moles. So we just use that total amount. So our answer is going to be in moles per second. And again, if we had concentration, we could do molarity per second, or again, usually we could also do minutes as well. So we just take 0.7 and divide it by 40, and that gives us a rate for the appearance of the product B of 0.0175 moles per second. And again, that's over the entire 40 seconds. If we looked at the first 20 or the second 20, we'd have different values. Now, we're not going to worry about, like in physics, if you're doing rates of, you know, going up or down, you have a negative or positive value. Again, that's just looking at direction. That negative or positive is showing you direction. We're not using negative or positive values here. We're just saying that this is the rate that B is appearing instead of making sure we have a positive value. And then we can look at the rate that A is disappearing by, again, we can go either the whole 40 seconds, the first 20, the second 20, whatever we want to do. But again, we take so this is for B. So for A, if we want to do the full 40 seconds, again, we take the concentration of A. So here we started at 1 mole and we went down to, well, that's boring. We'll do the same thing. We went down to 0.3 moles over 40 seconds. No, we didn't. So our change in A is 0.7 moles over 40 seconds. So again, that's going to give us the same rate. This is just in terms of the disappearance of A. So even though A is disappearing, we keep this a positive value. If we just wanted to look at the rate of the disappearance of A over like the first 20 seconds, we would take, so this would just be over 20 seconds. We would have 1.0 minus 0.54. So that would be 0.46 over 20. And that would be 0.023 moles per second. So for the disappearance of A in the first 20 seconds, it's disappearing at a rate that's quicker, that's faster than over the overall 40 seconds. And if we looked at the disappearance of A over the last 40, it would be even slower than the overall, because again, as we have less and less reactants, the products are going to be made slower, so the reaction's going to slow down. And again, we'll get into that more as we go through this chapter. Does that make sense? Okay. And like I said, we're not worried about are we appearing or disappearing? Should it be negative or positive? We're always going to make it positive. And just the wording, you know, if we're talking about product, we're talking about the appearance of a product. If we're talking about a reactant, we're talking about the disappearance of a reactant. So again, we don't need negative or positives like you do in physics. Okay, so like I was saying earlier, the rate does change with time. And this is from your book. There's a picture of, and you're going to use this on the homework. One of the questions on the back has you refer to this graph to calculate a particular rate at a certain time. So again, most reactions do not occur at a constant speed. Even you driving here, unless you have it on cruise control, which to get here, probably not. So unless you have your car on cruise control, you're not driving at a constant rate either. You're constantly speeding up, slowing down, even slight little changes if you're even on the highway. And that's the same with reactions as well. So again, as I said earlier, as the reactants get used up, the reaction will slow down. Because again, in order for a reaction to occur, we have to have collisions. And so if there's less, just like we said the other day, as we decrease concentration, that's going to decrease the rate. So with less reactants available, there's going to be less collisions to form products. So like I said, here we could have done, you know, all 40 seconds, first 20, second 20. So that's where it's really specific on what time frame are you looking at for the course of the rate that you want to calculate. What we call the instantaneous rate is the rate that's occurring at any one moment. If we were to freeze frame a reaction at a particular moment, what is that rate going to be? And so that's where this graph comes in. What we do to come up with the instantaneous rate is we use a graph, and again, this is change in y over change in x. This is technically slope, and that's what we do on the graph as well. What we do is we draw a tangent line through the point that we're looking at, the instantaneous, that one particular moment in time that we're trying to calculate the rate for. We find that on the graph, and then draw a tangent line through the graph, through that point on the graph, and then take the change in y, that's going to be our change in concentration, over the change in x, and that's going to be our change in time. So it's just like you do in math, figuring out the slope of a line. That's how we can figure out the instantaneous rate. I forget if this pen is my good pen. Now, if we're doing an instantaneous rate at time 0, like up in the very top corner at time 0, that's called the initial rate of the reaction. And again, we can draw a tangent line. That's what the little yellow triangles are, the triangle that the tangent line forms. So we just start at point 0 and draw it down. And you can make the tangent lines as big or as small as you want. I try to kind of make them match up with, the grid marks or the way the X and Y axes are labeled to make it easier to estimate numbers, but you can draw them as big or as small as you want. And everybody will get slightly different values for instantaneous rates, but they should be pretty close. So here, we're gonna determine the instantaneous rate for this compound C4H9Cl, that's what this is here, at time 300. And that is not the blue triangle. The blue triangle is doing it at time 600. So, let me draw this back up here. Where's 300? So here's 300. So there's our point in time that we want to figure out at that. If we were to freeze frame the reaction right here, what would its rate be? So I'm going to draw a tangent line, and you can make it as big again or as small as you want. And then I'm going to draw it over to the y-axis. This is going to be our change in concentration, and then dropping it down here to the x-axis. This is going to be our change in time. Okay, and let's see, what did I? So the numbers I used is, so for our change in concentration, we have 0.0. The way I drew it is 0.075 to 0.030. And for the change in time, what do I have? 550 to 100. So this would be 100 and 550. And our time is in seconds. This is in seconds. Okay, so just based on how big I drew my tangent line, again, you can draw it however big or small you want, but those are the numbers I got. So to calculate the rate at 300 seconds, I'm going to take my change in time, change in concentration over change in time. So we have the 0.075, and again, it doesn't matter which direction you subtract these, because we're going to make it positive. And again, 550 minus 100. So that gives us 1.0 times 10 to the negative fourth. And then in this case, for if you look at the concentration values, the units on the y-axis, that is in molarity instead of moles, so the capital M. So that means our rate then is going to be in molarity per second. And that's typically the most common concentration, but again, like we saw on the last chapter, on the last page, we could use just moles. It'll either be molarity or moles. And I don't know if I kept the right number of sig figs, if it was exactly 1.0 or not, but based on our data, we should have 2 sig figs in our answer. And again, everybody will get slightly different values. If you made a bigger tangent line or a smaller tangent line, you'll get different numbers here, and this will be slightly different, but it's still going to be in the ballpark of like somewhere in the 1 times 10 to the negative 4. Okay, so on the homework problem, everybody will have slightly different answers, but they should be fairly close together. So I don't know, what is that, algebra or something like that? No.
It's calc.
Huh?
I think it's calc.
It is it? Yeah. Oh. I remember calculus being a lot harder when I was your age.
Tangent lines.
I don't know. That's
Well,
not
you can
geometry.
also take like derivative.
Okay, how are we doing on time? Oh, we're doing pretty good. So, when we have a reaction and we don't know, and the stoichiometry ratios between the reactants are not 1 to 1, we have to do a little more work behind the scenes. So we can only use the stoichiometry ratios, you know, the coefficients that we use from balancing, if we don't know other data. So this is kind of the simplistic way that if we don't have data like here, like this graph or an actual data table showing us how the rates change over time, if we just have a ratio, if we just have a reaction and we just have concentrations, we can use the coefficients to help us. So again, the relative moles or the coefficients that we use for balancing, we can use those to give us approximate of how one reactant should change compared to another, or how it should change compared to a product, or vice versa. So again, this is if we don't have any of this kind of data here, we can just use the coefficients to figure out rates. Okay, so like here with propane combusting with oxygen, so we have C3H8 and O2 forming carbon dioxide and water, and then again we want to balance this, so we need a 3 and a 4 and a 5, right? Is that balanced? 6, 10, yeah, okay, that's balanced. So there's our reaction, and again we have no specific data to tell us, you know, how fast this reaction is going. But what we can do from just this basic balanced equation is we can look at the fact that this is well, let me put, you don't need the one up here. That the we can look at the fact that the oxygen is going to disappear at a rate of 5 times faster than the propane. So the O2 disappears 5 times faster than the propane. Or if we could look at the carbon dioxide is going to up here. So the carbon dioxide is going to up here 3 times faster than the propane disappearing. So when we don't have any actual data, we can just use the coefficients here to approximate based on, you know, we need 5 oxygens for every 1 propane. It's going to make 3 carbon dioxides for waters. So if we know the rate of one substance, like down here, we want to determine the rate of, let's see, do I have anything? Oops, sorry. Okay, I'll go back. If we want to determine the rate of any of these other substances, and we know that the propane is disappearing at 0.2 molar per second, so that's its rate. That's propane's rate. Then we can approximate what the rate of these other, either the disappearance of the oxygen or the appearance of either of the products, based on the mole ratios. So again, it's just your typical stoichiometry, like if we wanted to look at the disappearance of the oxygen, so we have 0.20 molar per second of the C3H8, and then we use our mole ratio of 5 moles of oxygen over 1 mole of C3H8. So multiplying that by 5, the oxygen is going to disappear at a rate of 1 molar per second. Like we said up here, it's going to disappear 5 times faster than the propane based on the mole ratio. Okay. Or if we wanted to look at the carbon dioxide, okay, the carbon dioxide we said is going to up here 3 times faster. So we do the same thing. If we do the, what was it, 0.2 molar of the propane, and then we multiply it by 3 moles of the carbon dioxide over 1 mole of the propane. That's going to give us 0.60 molar per second of the appearance. So carbon dioxide will appear at a rate of 0.6 molar per second. So again, that's if we don't have any actual data from the lab of what these rates are, we can just base it off of whatever rate of any one. It doesn't have to be a reactant. We could have, as long as we have the data of one of the substances, we can use the mole ratio to figure out the appearance or disappearance of one of the other substances. So if you can hang in there one more. Everybody have time to do this one last slide? I don't want to make it late or anything. So here we have decomposition of N2O5 forming NO2 and oxygen, and it has an instantaneous rate of 4.2 times 10 to the negative 7th molar per second. So that's for the N2O5, and we want to figure out at that instantaneous rate what would be the rate of the appearance of either product. And we'll just do one product to save time. You just have to switch the mole ratio to do the other product. Okay, so we have, what is it, 2N2O5 forming 4NO2 and O2. So we'll do the NO, so we'll figure this one out first. And we have 4.2 times 10 to the negative 7th, and that's in molarity per second. So if we set that up and do a little stoichiometry, this is the N2O5. Then we just use our mole ratio of 4 moles of NO2 over 2 moles of N2O5. And so what do we get? So we get 8.4 times 10 to the negative 7th. Molarity per second of the, what was that, NO2. So that's the rate that the NO2 will appear. It's double it because this is 4 over 2. And if we were to look at the oxygen, what would the oxygen be? It would be half that, because it would be 2 over 1 over 2. So it would be half of this amount. Okay. So again, that's if we don't have any other data. And for other than using on the back here, it has you use that graph from before to calculate that. The rest of these just use the coefficients. Okay. All right. Well, good job. Drive carefully if you have to drive somewhere for your J turn. For some reason, rain makes